Hey, yeah, my name is Helen. I'm a PhD student at Mila, Montreal, and I'm here for an internship with Antonio. And I started in January. I'm almost at the end of the internship here. So yeah, I mostly work on optimization in deep learning, and this is a work that it's still in progress. We submitted to an ICML workshop. So hopefully we'll gain some ideas of how to turn it into an actual paper. And yeah, for the half of people who already listened to this talk, sorry about that. But yeah, so it's titled Signal Imbalance and EO Conditioning. And it's in collaboration with Francis and Fred at INRIA. So it is kind of known in the field that Adam performs better than SGD on language models, transformers, and such cases by a very large margin. And so there's a lot of work in the recent years trying to figure out why there is a gap in language model and if we can sort of capture what are the structural properties that Adam is taking advantage of. Um, oops. So for example, one thing that people looked into in these neural networks is that um, Adam's benefit is mostly in the first and last layers. So there's some work, without going into details, sort of like only use Adam in the first and last layer and use SGD like things in the middle, and it can recover almost the full advantage of Adam. And so there is some sort of structure in the first and last layer that is worth paying attention to. And most recently, there is a Twitter hype about Muon. Well, it's not just a Twitter hype. People actually started using it. So this new optimizer named Muon is, I would say, like one of the few ones after Adam that actually made it out of just the academia paper that is being used in large scale and proven to be work better. But this is an optimizer that mostly is beneficial in the middle layers of the neural network. And so, yeah, I would like to understand what structure is Adam and Muon taking advantage of and why a certain optimizer benefits from first and last layer and some from the middle layer. And there are some important existing work that this paper is based on that sort of try to explain why Adam has the advantage in SGD in language model. So in the very left panel of this figure, it's showing the characteristic of language data, which is that the class distribution is imbalanced. So what that means is, for example, there are a few words such as the or that appears very, very frequently in language data. But there are most words like mitochondria or like any other word that appears at much less frequency, but they make up the majority of the text data. So this structure is called heavy-tailed. So when it's heavy-tail imbalanced, we can see that Adam does better. And specifically on the right two panel, this is separated into different frequency groups of the classes and how the loss goes down for each class. And so here you can see that SGD does pretty well in the class frequency, but struggle to lower the loss on the low frequency. But Adam is able to make progress in the low frequency classes as well. So um, this kind of makes sense because in the first and last layer, the coordinates correspond specifically to like specific tokens. And so if you have imbalance in the class distribution, then the first layer or the last layer that's coordinate corresponding to the next word would suffer from this problem. And Adam is able to make progress here. But in the middle layer, things are a bit more complicated because the coordinate corresponds to the features or some arbitrary combinations of the classes. So there's still imbalance, but it's no longer a class imbalance. And we want to understand, so what structure is there in the middle layers as well? And another observation that people have is that this only happens at large batch. So if you have a small batch size, the gap between optimizers is a lot smaller. So starting from a small example, if we just simplify everything down to a background model with square laws and try to predict why. So here we can do some analysis that reproduces previous examples. Basically, on the left, that Adam and Muon is able to make progress, GD does very bad. And if you separate them into the frequency classes, you can see that GD struggles on the low frequency, Adam and Muon makes progress there. And one of the important things to notice is that Adam's benefit depends on the coordinate alignment. So what I mean by that is that when you have a function that the condition is sort of like aligned with the coordinates, then Adam is able to go straight to the minimizer. But if you were to rotate this function, then Adam's trajectory would change and lose its advantage somewhat because of its element-wise division. And so this sort of becomes an issue when you're looking at the inner layer of the network. So this example, we kind of want to mimic how an embedding layer would work by just using a random rotation to mix up the coordinates. So if you apply this random rotation to this very simple example, then you can see that Muon is still working pretty well because its rotation equivariant. So the trajectory or the speed of convergence doesn't change. But Adam here suddenly loses its advantage. So this sort of gives you an intuition of why it is the case in the middle of the network that Muon is more beneficial, but Adam is not. And we have come up with a framework to capture what is the imbalance in the middle layers. So it's sort of a generalization of class distribution imbalance, but we call signal frequency imbalance. So the definition sort of goes, if you look at the example, per example gradients, if they were able to be separated in a way that's like into a few groups, like let's say group S1 to group SK, in such a way that within each group, the gradients are highly correlated, and so across groups, the gradients are almost orthogonal, then you have this class signal frequency. And if these groups are of different sizes, then we call it like signal frequency imbalance. And so the intuition of this is just that you have bigger clusters of gradient directions and smaller clusters of gradient directions. And in between these clusters, not too correlated. And if you look at the example graph matrix, it will have a sort of a block diagonal structure that some blocks are larger, some blocks are smaller. And so in the previous example that I told you, you can actually compute this exactly, that up to some permutation, the data graph matrix is block diagonal. And this corresponds to the gradient direction also being block diagonal. That's the large gradient direction corresponds to the most frequent example. And so we kind of want to see, so how, first of all, is this true in a language model or like neural network in general? And second of all, if this is true, what does this mean to for the optimizers? And here, why this is interesting is because the notion in traditional optimization of how ill conditional work is often comes from magnitude imbalance, which means that the data itself, so every single data has sort of a magnitude. Like imagine if your feature is from different, let's say like a year of a car or a model of a car, like these are very different magnitudes. But so every single data is imbalanced in that sense. But frequency imbalance is when you have every single data is not a problem, but if you have a group of data, then the frequency is imbalanced. So what this means is that you will have still the same hashing, but the behaviors of the optimization dynamic will be different because in the magnitude imbalance case, it doesn't matter what batch size you're using, you're always having this ill conditioning, and you want to use sort of the same preconditioner to fix this conditioning. But in the frequency imbalance case, the optimal fixed preconditioner to use to fix this problem depends highly on the batch size. So if you only have one data, you're not actually ill conditioned. The ill condition only comes out when you have a lot of data and you're doing things like SGD to average the gradients of the data. And so the gradients of the less frequent classes or groups are being overlooked. And yeah, this sort of checks out with what I previously mentioned about the gap only comes up when the batch size is large. And yeah, some small experiments on a two-layer neural network. What we do is here we treat the examples as this sort of like diagram examples just to look at what the structures are. And we compute the gradients and sort of sample the gram matrix between examples and see if the structure actually exists in the network. And so here you can see on the left panel of both graph. So the left is a self-attention output projection layer, and the right is a second MLP layer. And so on the left panel, you can see that the graph matrix does exhibit this sort of block diagonal and also frequency imbalance structure. And on the right is the top eigenvectors of the weight graph matrix that also corresponds to the classes. And yeah, there's some more analysis in the paper that I won't have time to go through, but if you look into what these clusters actually represent, there are also semantic meanings of different layers. And so you can sort of have a look on what the features are learned in each layer. And yeah, so to quickly conclude, we define frequency imbalance from gradient clusters that creates EO condition at large batch size, where mini-batch averaging suppresses the rare directions. And this sort of explains why Adam is better in the first and last layer and why Muon is better in the middle layers. And with this information, there's a lot of things one can do, such as investigate whether similar structures can appear beyond language model, understanding how this imbalance evolves during training, like beginning and the middle and the end of training. So study how batch size scaling works, or like the notion of critical batch size is defined for non-Euclidean methods like Adam. And maybe we can even design better optimizers that exploits this imbalanced gradient cluster structure. So here's the paper QR code. Thank you.